Our next speaker is Dr. Mike Banach from FlexEnable Technology, a spin-off company in Cambridge. He's probably going to tell you all about the spin-off. Mike was a student of Richard Friend at the Cavendish. In what group was it? Oh, optoelectronics. And Richard sent me some information about Richard, but I'm going to spare his blushes and not share that information with you. So I just ask you to welcome.
Right. So everyone can hear me? Yeah, me all good? Excellent. Oh, wait, I have to stand by the camera, is that right? Yeah. Good. Excellent. All right. Well, first, thanks for the opportunity to speak. I was telling John at dinner that it was really fun to kind of take a step back and think about what we as a business have done over the last sort of 20 years. And you kind of look at it from a big picture. And so I've really enjoyed preparing for the talk, and I hope you enjoy listening to it. I've been in Cambridge for close to 25 years now, and I'm always amazed at the quality of talks and seminars and stuff that are available. So it's great to play a small role in contributing to this. So thanks for this opportunity. Right, so we'll get into it. So first, a bit about me. I'm American, as you can probably tell. Originally from Cleveland, born and raised there, but did a undergraduate degree at the University of Cincinnati. And then, as John said, I did a postgraduate degree with Richard Friend at the University of Cambridge. I was in what at the time was called the new Cavendish. From what I understand now, there's an even newer Cavendish, and so I think I was in Cav 2, but I think there's now a Cav 3, and we'll see where that goes. But I jumped to a company when I graduated. That company was called Plastic Logic. It has subsequently changed names, and I'll get into that as we go. But ultimately, I've been kind of working in flexible electronics now for over 2 decades. At FlexEnable, there's a team of about 50 engineers, and we've been working on several generations of flexible display technology and some other applications, which I'll touch upon at the end. And what I really chose to focus on is that transition from doing things in a laboratory to doing things in a factory. And that's really what I think our specialty has really become at FlexEnable. And so I want to spend some time on that. So a brief outline. So first I'm going to talk about organic transistors. That really is the foundation of what we do at FlexEnable. Everything was built from that basis. And then I want to talk about how we took those devices and started manufacturing those in higher volumes. I'll then come back and focus on the options for flexible display technology and why we chose to focus on the one we chose to focus on. And I'll end with some of the new things that are happening in the lab, which are actually pretty far away from displays, but quite exciting. And then I'll just offer a few closing thoughts. So first, the transistor, the thin film transistor. It is a thin film. It is a 3-terminal device. A very simple device. It's the simplest type of switch you can get in electronics. So effectively, you just apply some voltage to the gate electrode, and that allows you to control the charge carriers in your semiconductor. And then when you put a voltage across the source to the drain on the top, you can then get a signal or a current that flows. And so effectively, you can modulate the current in the drain, to the drain, by the gate voltage. A very simple, device, very powerful device. For everybody that's probably watching us on Zoom, you're staring at millions of these devices because they're basically the basis of all displays. You've got millions of these that are controlling every single pixel on your display. So it's a very powerful but simple device structure. Most of the conventional thin film transistors were made out of ceramics and metals. So silicon, of course, was the big one. There are others. So like a lot of people are doing it on different type of oxide materials these days. But in the 1970s, researchers started discovering that you can get certain polymers. Polymers are obviously these long entangled molecules, usually quite disordered, and they found out that they can conduct electricity. And it was the reason for that, of course, is that you had specific polymers that had double bonds in the chemical structure, and that electron associated with the double bond was able to dissociate and move to a certain degree. And over the subsequent 40 years, obviously the understanding of this phenomenon grew, and additional polymers were synthesized, and now you have things that can exhibit, as Yu-Chi showed, electroluminescence. There's you can do light harvesting in photovoltaics, and of course what we're focused on is the transistor. Cambridge is a great place to be if you want to do flexible or organic electronics, primarily due to Richard and his colleagues over the years. So the Cavendish Laboratory has been on the on the innovation, the world leading innovations now, pretty much since the beginning of this field. And so they've got a great track record and a great group of people working there. So yeah, so there's a very good reason why our company is based in Cambridge. Yeah, so this is now getting into effectively a marketing slide for FlexEnable. So this is an organic version of that thin film transistor. Very similar structure. You got a gate, you got a source and a drain, but basically all the ceramic materials in the device are replaced with more durable, more flexible plastics. Plastics open up different manufacturing techniques, so you could print, you can kind of process things from solution as opposed to do the more sputtering and the things that are more common in the microelectronic industry. Crucially for us, the process temperatures for these plastics are all or can be below 100 degrees C. And this gives us a wide range of materials that we could work with as our substrates. And so, yeah, so this is basically the basis, the structure from which we're working from. However, the chemistry itself is very sophisticated. Certainly much more sophisticated than when they started. They kind of learned a lot more of how you kind of synthesize these molecules, and where to place the double bonds, how they can kind of orient themselves to enhance charge transport. I would say there was two kind of real big surprises for me, because I mean I've kind of been following it obviously for a long time in this journey, and number one, I remember being in the labs in Cambridge in the university, and really what you're trying to do is create these polymers with as much order as possible. You're trying to get crystalline structures, because the idea is that the crystalline structures, even if the molecule in general was a bit disordered, if you had some crystalline areas, that would really enhance the charge transport. So that was really the target at the time. And of course it does in a way, improve the charge transport, but it does come with a penalty. The crystallinity is actually can lead to a lot of non-uniformities. And so, what the most sophisticated materials now is that they've gone away from searching for that crystallinity and actually are looking for, more nuanced view of getting a little bit of order, but actually, sticking with a broadly, amorphous film. And they're the ones that give the best performance. The second one is that, the field was, primarily focused on the semiconductor, the one that, basically, transports the electrons, the holes during the operation. However, what was equally important was, the dielectric material and the material that goes directly on top of that semiconductor, because that's the material that obviously, controls, whether or not these charges get trapped or any. So it was equally important to come up with a compatible dielectric as it was to come up with a very powerful semiconductor. For us, that meant that the dielectric really needed to be, low K and inert, so basically just a very inert material that's not going to, attract any charges, not going to trap any charges. And so that has basically become the the foundation of the material stack that we've been using at FlexEnable. And these are, basically the curves that prove, the state of the art performance of the materials today. I'm not going to go, painstakingly through this, but just to say there's three kind of critical attributes when you're looking at, these kind of switches or these transistors. Number one, of course, is the mobility. That's maybe the most obvious. So how fast is it? How fast can you get charges, moving in your material? And we have a mobility of 1.5. The only thing to compare that against would be an amorphous silicon transistor of a similar type of structure would have a mobility of 0.5. So we're basically 3 times better in that factor than amorphous silicon, which is kind of the ubiquitous technology for displays. The second is uniformity. Especially if you think about a display, if every pixel right next to each other has a different performance, then you are going to see that in some way, shape, or form. That was why, kind of using some of these more amorphous materials were so important for our display applications. And you can see that we have, this is, threshold. So this is when the device turns on, and it turns on, within, a fraction of a volt, which is, very good for a display application. And finally, stability. And using the industrial standard both for electrical and thermal stability, you can see that we get very small shifts in that turn on voltage when you apply these sort of stresses, which again proved that we had a transistor that is capable of commercial applications. So those were kind of comparing it to what was, kind of you're comparing it to what existed, but this is obviously what differentiates us from what you can do, at least with silicon on glass. I mean, this is one of our devices. This is actually quite a dated video, but this is one of our transistors that have been, flexed. We've done it, tens of thousands of times, and it is very stable. This is about a centimeter bend radius, but we've been able to get down to 100 microns, so a tenth of a millimeter, and it just that shows that these devices are fundamentally stable to that sort of mechanical stress. More recently, we've kind of really been focusing on another benefit and another way where we can differentiate ourselves from, kind of the more ubiquitous silicon technology. And that's really through, by actually are 3D forming the devices. These are quite subtle. I mean, this is like maybe a 1% stretch that we're putting on the device. It's important for some of the applications, which I'll allude to at the end. But it also just kind of gives you understanding of these things are just mechanically much more durable, much more flexible than electronics that certainly predated or are more common in the market. So that's the basis, so that's the organic transistors, what we have used to kind of build a business. We were using that and finding applications that can benefit from that performance. So of course, initially you spend a lot of time getting the device right, making sure that you get the performance and the stability and all that, but then eventually you have to figure out how to manufacture it, and that was really became an interesting journey in itself. And so now I'm going to kind of spend a little bit more time focusing on the company and how that story has emerged over the years. So the company that was founded in 2000 was a company called Plastic Logic, and the founding vision for that company is that people were aware of organic semiconductors. They were very efficient at turning electricity into light, so that was kind of getting a lot of interest for displays, and there was companies looking at turning light into electricity that was gaining a lot of interest in solar cells. And so we decided to take on the challenge of looking at the field effect conductivity that can be made into switches. So we showed that obviously these devices are flexible, they're durable, they can be molded, and also, as I alluded to previously, they can be printed. Right, you can dissolve these materials in solvents. You can print them like an inkjet printer. You can basically print them like you print your newspaper. Not that anyone buys those anymore, but it was kind of using that sort of technology. So the founding vision really was that we could bring the functionality of the transistor at the cost of the printing industry, right? So it can be as ubiquitous as newspapers, but as useful as a display, or name the electronic device that you're aiming for. So we had a great technology. We were thinking about how to make it, and so the next step is who cares, who wanted these devices, what can you use them for? And so the first several years of the company was spent just in this market discovery phase where you're looking for the application. And I think it emerged relatively early on, where the best application for the organic transistor was a backplane, an active matrix backplane. So basically you can put them in an array, and that array of transistors can either drive an image or it can read an image. So you can use it as a display, you can use it as a sensor, but that array really did emerge as the number one application for these sorts of devices. However, if you think about kind of displays, and this is even back in 2000, 2005, when we were kind of considering these things, the pixel sizes were incredibly small, and subsequently have only gotten smaller and smaller. I mean, so people have really tried to make devices of just higher and higher resolution, which was a massive challenge for conventional printing technology. So when you think about your newspaper, it's nowhere near the resolution as your smartphone or those type of things. And so it was going to be very difficult to actually, build relevant, commercial, devices using, conventional printing techniques. So that was the first of many pivots that we've had as a business, where we, started, focusing on, our unique materials and the class of materials that we were developing. But instead of using, unique manufacturing techniques, we, pivoted to what would be conventional, manufacturing techniques, and basically using our materials on the same factories that you would make a glass display. And that was quite successful. So, here's basically a pictorial, version of how, that display technology developed over about a decade there. This is, using e-paper displays. That was kind of the first type of display technology we were working on. You can see there in 2002, we had 16 pixels, about 4 of them working, something like that. But by 2011, we had 3 million pixels, and all of them are working. So it just shows that with effort and good science, you're able to kind of take that journey and really mature the technology. But it didn't come for free, of course. I mean, we needed to do that in the right environment. So you needed a factory. We were doing most of our work in labs, and we needed to build a factory to do this. So this is just a quick video of a factory that is well, it's a flat panel display factory. So this is how flat panel displays are made. So you have massive glass plates that are automated in their handling. And the only thing that we do different from a conventional glass display is that our first process step, of course, is to laminate a piece of plastic to the glass. And then we take it around a very similar set of equipment using different material, and end up with a result that is plastic and flexible as opposed to glass. But you can see it's fully automated. There's no hands that touch the product, and so that was really the benefit of kind of moving to a facility like this. And for people like myself who are coming from a pure research background, we got a whole team of us got very familiar with terms like cycle times and yield, and it was you almost changed the whole vocabulary of the company over those few years, which was really quite exciting to see. And the factory and then was a success. I mean, we were able to make wonderful looking e-paper displays. I mean, here's an example of one that we put into it seemed like a folding book concept, and we had loads of product concepts and products with customers that we were working on. It was a so a wonderful technology success. However, commercially, it was quite difficult, and the difficulty was the market for these type of displays, these e-paper displays, just wasn't large enough to justify a bespoke kind of standalone factory. So unfortunately, the factory itself wasn't a commercial success, but technically it was very successful. So that really gets us into FlexEnable and why why we're called FlexEnable, how it was founded, and then the journey that we went on with displays since then. So as I said, the first company that was spun out of Cambridge University was This company was Plastic Logic. It was really focused on OTFT process technology. FlexEnable was spun out of Plastic Logic in 2015. And its business model was slightly different. It was not only looking at process technology, but also a materials business. So we basically, changed the model a little bit. And also we looked at a broader range of applications. It really allowed us, because Plastic Logic was very much focused on e-paper devices. FlexEnable became focused on other applications that you can do with these devices. So at a glance, we're still, obviously we were still founded from the University of Cambridge. The academic founders, remain the same. We did hire some experts in Taiwan to help us with some of the manufacturing, because our business model now became doing our processing in existing factories as opposed to building your own factory. We retained all the intellectual property. We, as I said, had the materials that we were selling. And importantly, we had the prototyping facility, which is still located in Cambridge. So it's just on the north part. It's in the Science Park on Milton Road, which allowed us to do quick prototyping, which allowed us to, basically, work very directly with end users for these sorts of applications. But the question became, sort of what, I mean, you can do whatever you want, but what would be, what is the best application for, OTFT again? I mean, we basically gave ourselves a chance to revisit that question. Displays still seem to be the most compelling market, but we knew that the e-paper, market was too small. Whilst it had, great attributes, it lacked in its ability to kind of drive color, and it wasn't able to do video right, and so therefore it always remained, a small market. If you go to the whole other end of it, people that have been following the display industry would probably hear a lot about OLED displays, organic light emission, and it's been a fantastic technology for now, quite some time. It has great video, great color performance. It's got the potential and now the reality of being very flexible. I mean, people who carry around these phones, I mean, can prove that. The problems with OLED from our perspective is that it is difficult to drive. If you think about an OLED, you have to supply a constant current to the OLED, which is much more challenging from a circuit design perspective, as opposed to some of the e-paper or the liquid crystal displays, where you just need to basically set the voltage. And it's also at the time when we were really considering this, the questionable, the scalability, how big can you make an OLED, especially if it was flexible, which got us thinking about liquid crystal displays. Now liquid crystal is still the most dominant display technology today. It's probably still 80% of the market, even though people spend most of their time talking about all the other displays that are can be used. Liquid crystal was kind of the first thin film display technology, and it's still the most common. It has proven to constantly innovate, and before you'd always talk about your liquid crystal displays being poor off-axis performance, but then of course they came up with new modes that fix that. So they had problems with ghosting, and they've came out with new transistor technologies to improve that. So it has proven to be a very durable and flexible technology in the sense that, it is constantly improved over time. However, certainly when we were considering, this question several years ago, no one would really imagine of making your liquid crystal display plastic or flexible, right? I mean, it's effectively a cell. It's a liquid crystal cell that you're using to attenuate a backlight. And so the idea that you're going to have this liquid cell and you're going to flex it was not really seen as practical. And so everyone that was in this industry was basically saying, well, if you're going to go flexible, you have to do a different approach. So that was so we decided to take on that challenge, and there was a couple reasons. So first is, just think about flexible OLED. At the time, flexible OLED was just emerging. It's now, of course, fully emerged, and you see displays all over the place. The foldable phones and curved phones. They look fantastic. The reality is that this technology is being developed by a relatively small number of companies that have invested a lot of money in it. And that they're making devices which are commercially relevant. I mean, they're expensive. They certainly make sense in high-end phones, but it's still not kind of the same ubiquitous nature as the LCDs. So we were thinking about OLED, and of course, there was a couple of reasons why we didn't do OLED, and the first is that, well, we tried. We tried to do OLED, and this is one of our OLED displays. You can see it was I think it was about 100 microns thick, and you can see you can wrap this display around a pencil. The problem was it was very technically incredibly challenging. It was very hard to sort of make these devices. That in itself is not a reason to stop, right? Is not because it's hard you stop. But the second reason is probably more compelling, and that's business model. For us, the business model was to go into existing factories, right, and to sell them new materials, convince them to do unique processes in their factories. Now, if you have an OLED factory, you're not going to try to do new stuff. I mean, you've got plenty of market, and you're just going to try to make as much as you can and sell it. So, and there's not as many of those factories around. There's a very small number of companies that actually have mastered the technique of making those high-end OLED displays. So for us, the bigger market opportunity was actually to go to the people that were making liquid crystal displays. I mean, there was a lot more of them, and they were going to be a lot more hungry for unique technology. So we really targeted those as a customer for our, basically our process technology, and of course the materials that enable that. So that is really why we focused on, what ended up becoming plastic liquid crystal displays. Yeah, so, so what do you do? And once you kind of make the decision that you want to, work with, plastic liquid crystal, what do you do next? Well, I mean, the first thing you do is you brand it, right? So we had to come up with the right name. So we figured we were competing against OLED, so let's call it organic LCD. So we were OLCD as opposed to OLED. So that was a good start. And then we went to the more practical steps of how you build it. And so what you can see is two cross sections here. One is what is a conventional, sort of silicon, cross section of a conventional silicon display. And on the left is, what is the cross section of, one of our displays. And those that are kind of skilled in the art and kind of know a lot about displays would be surprised how similar they are. Because the point is that for liquid crystal, you need a backlight, you need polarizers, you need color filters. All those things are the same, regardless of how you make it. And actually, we were making a few subtle changes to actually get what is a massive improvement in the form factor. So we were basically changing the glass with this plastic substrate. I mean, it ended up being a bioplastic because of the the specific optical properties. We had a slight change in the structure of the transistor. Instead of doing a bottom gate, we use a top gate, but that's a very subtle change. And primarily, we changed all the ceramic and silicon materials with our organic materials. But then I come back to this point that crucially, we went to these factories and we adopted a process temperature that was below 100 degrees C. And that ended up being a really important step for us. And why it was so important was if you kind of remember that video that I showed about the factory, right? You laminate, when you make one of these displays, you laminate the plastic to the glass, and then you take it through all the processes, and at the end you have to take it off, right? Now they've developed an approach to do this for these flexible OLED displays, and it's primarily it's around coating a very thin polymer film, and then you use some sort of laser approach to remove the plastic from the glass, which is works very well. The problem is if you have a liquid crystal, remember you've got a liquid cell, and so you've got two pieces of glass. You got a glass on the top and you got a glass on the bottom. And so now actually removing the plastic becomes a little bit more of a challenge, especially if you think about the size of some of these display factories. I mean, they're talking about glass around 2 meters by 2 meters. I mean, they're massive. So the ability to actually remove two pieces of glass which are separated by 100 microns or so becomes a massive problem. And so our process temperatures allowed us to use some very conventional thermal release tapes that made this demounting quite elegant. And so here's a video of how it works. I mean, so here's an example of how you kind of laser scribe it, but then you just take the whole plate and you put it on a hot plate, and these chips, and you can kind of imagine those being displays, they would just pop off and just pop off the glass. Now, if you have two pieces of glass, of course, they don't kind of pop off to the same extent, but they release themselves from the glass. You can take one sheet off the bottom, one sheet off the top, and you're left with your display at the end. So it was a very elegant way of manufacturing plastic liquid crystal cells to a very high resolution, to a very high precision. And so, it was a very, important discovery in, our journey. And so, after a lot of hard work, and we eventually were able to show that this was all very practical. So here's one of the displays that we actually made in our prototyping facility in Cambridge. I mean, we get a few lineouts and stuff due to some manual handling that we have to do in our lab. But you can see this is a 4.7-inch display, and it's got the same front of screen performance that you would expect from a glass display that you would have had. It's actually using a backlight from an old iPhone, and those are actually thin enough to be a bit flexible. So we've got kind of a relevant pixel density, a relevant resolution. So these are all very common specs for a display today. So it's effectively doing everything as your glass display, but it's only a couple hundred microns thick, and you can wrap it around a coffee cup. So it's bringing different attributes to the market. So now you can go to the market and ask, so what is kind of better about your technology? Well, why should we you use your OLCD as opposed to a glass LCD? First of all, it's 100 times. Sorry, it's 10 times lighter. 4 times thinner. We showed that you can curve it to a much greater degree than glass. It's much easier to kind of shape into different sizes. You can just laser cut it down to whatever size you want. And the cost was interesting because it kind of go back to that cross section on the display. A lot of the cost for the two devices were actually the same. I mean, in both cases you have a backlight, and in both cases you got a polarizer, and in both so it's a relatively marginal delta in the process in general. And so ultimately, the cross change is very, very small. And so, we were able to get, cost competitive quite quickly. Basically by, kind of living with, or, kind of taking advantage of the existing supply chain for, liquid crystal displays. So now we position ourselves as sort of a complementary technology to OLED. We're not, so we accept that, OLED is a wonderful technology. It's obviously showing itself in, many different, consumer electronic applications, phones, watches, even some tablets and whatnot. But, for anything that needs longer lifetime, larger area, brighter displays, that's not really what OLED's good at. That's what liquid crystal is good at. And so we could basically enhance, those applications by making them plastic, making them a bit flexible. And that is, a very large market, for FlexEnable. I wanted to focus on, that we've got, loads of there's loads of slides on various applications we can do with our, LCD technology. And so I'm not going to go into all of them, but there was 2 that I did want to focus on because I think they basically illustrate the point. The first one is this using them for, automotive. I think it's not hard to imagine why automotive companies would be interested in a more flexible display. I think that's easy to see. Why wouldn't they be hopping all over the OLED? Well, it's because brightness is really important, and brightness is actually one of the limitations with OLED. Also, long lifetime is one of the problems with OLED, and obviously for a car, it needs to be able to last quite a long time. So, this is really a market where LCD thrives, and so therefore organic LCD has a really good selling point for that. Another one is, and I think this is a neat story because it really kind of showcases how existing technologies can really fight against emerging technology. So people that are really into the details of the display industry will know that OLEDs are always talked about in terms of this high contrast. And the reason they get high contrast, of course, is that they get a very low black. I mean, when you turn an OLED off, you don't get any light, so your black is infinite. I mean, you get a very black display, which is not the case for liquid crystals, right? For liquid crystals, you have a backlight, and so the way you get a black state is by turning that black light off, and you do that with these liquid crystals, which aren't perfect, and so you get light leakage, and so that's often why the liquid crystals have a compromised contrast, where OLED has a wonderful contrast. The benefit of liquid crystals, of course, is that you can up that backlight as much as you want, and you can make that display as bright as you want, and there's really no penalty. There's no penalty to pay. So you can get a bright display, but often you're compromised on contrast. OLED can't have the brightness, but you certainly get as much contrast as you want. But with our approach, you can make the display so thin that you can add a black and white one below the color one, right? So you effectively have a black and white display that is enhancing the contrast of your color display. And so this is really a way in which you can, get the best of both worlds. I mean, you can have, a very bright, high contrast television. And the only way you do that is because, of course, if it was all made out of glass, then kind of the parallax of the two different pixels on top of each other would be so far off that it just wouldn't, especially with these high definition televisions that are out today. So you really have to have the display as thin as possible, so almost intimately, ours we can get down to about 30 or 40 microns, and then that basically gets you into a point where you can explore some of these features. So I just think that's just a very interesting way of something, of course, because we're always talking about flexibility, we're always talking about durability. In this case, we aren't taking advantage of any of those things. It's just the fact that it's super thin, where we're being able to exploit a different market. So yeah, so that's kind of where we are with our display technology. I mean, we have companies, manufacturing partners in Asia that are kind of good at making glass displays that are now converting a portion of their facilities to making plastic displays, and I suspect we'll be making those more available to the market in the coming years. But we've got some new development in Cambridge. We're really focused on new technologies, new things that we can do. So I thought I would take this opportunity to highlight a few of those as well. So I just spent several slides talking about organic liquid crystals. When we were out talking about to our customer base on our full color displays, they were saying, oh yeah, those look fantastic, but can I just use just the plastic liquid crystal cell? I have a few applications for those. You seem to be really good at making just high quality plastic liquid crystal cells. So I have some applications for you. Can you help me explore those? And so we have looked into it, and there ends up being several very interesting and potentially quite commercially exciting areas. So I mean, the first is down here at the bottom is the LCD, which I already explained, OLCD. So if we go clockwise around, the next one here is this automotive smart window. So if you think about your car, the sunroof, of course, it's not flat. It's got some sort of 3D bend on it, and so the only way you can really integrate any tinting into that is by putting some sort of plastic cell between the pieces of glazed glass, and doing that with a liquid crystal. A liquid crystal, of course, can tint. They've shown that very well in the display industry. And so that becomes a very interesting application for us, especially if you've got the ability to manufacture these large area plastic liquid crystal cells to a high quality. This is a very good market opportunity for you. So we've been exploring that, and I'll show you some examples of that. Of course, everyone, all the big consumer electronics companies on the West Coast are talking about AR, VR headsets, the new generation of devices, and you can use these tintable films to help those product concepts as well. And I have a slide to kind of explain that concept after this. The one that I love is the tunable lens. So we can use these flexible plastic liquid crystal cells and use those to actually focus light, and that has become, again, a very interesting application for some of these headset makers. And finally, the one that's maybe a little bit more straightforward to think of is these e-privacy screens. If anyone who had one of these original liquid crystal cells would realize that, in the first versions, they were awful off-axis. Well, if you really lean into that and take advantage of that, you can actually, build that into your backlight, and basically build in a switchable privacy function. Now that only works though is if that is built out of plastic, because if you're going to add a whole bunch of glass and make your device much thicker and heavier, and it's not really what people want. So we've got people that are interested in what is a very simple liquid crystal cell. There's nothing sophisticated about it, but again, just the fact that it's plastic brings it into commercial relevance. So yeah, first, probably the easiest one to conceptually understand, tintable films. I mean, this isn't hard. You basically just put a dye in the liquid crystal, and then by switching the liquid crystal, you get that dye to turn on and off. And here you can see that we have tintable films that have a dynamic range, or kind of in the dark state, you get down to about 1% transmission, which is quite good for a car roof. And then in the clear state, it gets up to close to 35–40%, and that again is pretty much exactly what a lot of these automotive companies are looking for. So yeah, this is quite a good area for us to explore. And again, not a lot of paint. It's actually quite easy for us to make these sort of devices after you've been making full active matrix displays with a whole bunch of transistors. The second one is the spatial dimmers, and I said I'd come back to this. So it's really interesting. For these augmented reality headsets, you have to of course use them outside, and you have a virtual image that is being projected by a light engine. Now when you're inside, that light engine is competing with the ambient light in the room, and it's you can do that. That's possible. It's capable of doing that. When you go outside, you're competing against the sun, which is not possible. So it's almost impossible to basically create a light engine that is going to be bright enough to see it relative to the sun. So the way the way you defeat that is basically dimming the sun, right? So you put a dimmer on the outside of the headset, but that dimmer has to be tunable, of course, because when you come back inside, you have to turn it off, and so you need to have a tunable dimming capability for these headsets really to hit the ubiquitous use cases that they're envisioning. What we were surprised at is that a lot of these companies also want these dimmers to be pixelated, right? So that way they can shoot their light engines in specific areas in your site and have some things that are dimmed and some things aren't, and they can really enhance what they're trying to do with these devices. And so that, of course, is a wonderful product for us because it's effectively a display. We've been spending a lot of time with displays, but it's for a completely different use case. That is, those are some of the most exciting projects that we have going on now. Yeah, and the final one that I will talk about are these tunable lenses. Yeah, again, for these headsets, the augmented and also the virtual reality headsets, they have them. The optics in these headsets are fixed. So the virtual images are always at about 2 meters. So you always have the images kind of so you can see them at 2 meters. Or so the real world's always at 2 meters. If you're trying to do virtual images that kind of come closer than that, it starts to really tire your eyes, and that's really where people start talking about getting the headaches, and when you use these sort of devices. So the real holy grail in this industry is if you can come up with a tunable lens which allows you to electrically adjust the focus of those optics relative to the content that you're trying to show, which allows your eyes to accommodate for that for that virtual image. With a liquid crystal cell, you actually have the ability to do that. So if you think about a lens, normally for a lens, the way you get it to focus, of course, is you change the thickness of the material as a function of radius, and the light ends up focusing. For a liquid crystal lens, you change the refractive index as a function of radius, and you keep the thickness the same. And so we're able to make very powerful lenses that are actually very, very thin. And we have been able to show that you can get relatively powerful, these are optical power, so this is 3 diopter of optical power using one of the liquid crystal lenses. And again, this is a device here that's only about, I don't know, 100 or 200 microns thick, so it's a very thin, whatever it is, 4 or 5 sheets of paper stacked on top of each other, and you're getting 3 diopters of optical power, which is pretty significant and tunable within that range. So I'm quite excited about where those devices can go. So that's it. That's all I've prepared. I've just maybe a couple closing thoughts. Obviously, kind of talked a lot about taking the journey from the laboratory to the factory, and how that is complicated. But just to say, in a research environment where people a lot of time focus on that eureka moment, on when when the new development was made, and of course that's rewarding. Of course that's great. I just like to say that the that more complicated journey is also intellectually very rewarding. It's a very interesting ride. Of course, you've got commercial things you need to worry about. There's technical realities, and more and more recently there's geopolitical things that you have to consider. And so it's a very intellectual, rewarding experience. And so just wanted to make sure that that came across. The second thing is, kind of, when you're in these kind of, technology companies, and you kind of probably saw a little bit of a flavor for that in the talk, is that, there's, kind of this dilemma between, focusing on what is going to be the big market opportunity, and, making sure that you're ready for that, versus being responsive to all the opportunities that could potentially be there for a business, because of course the world is filled with opportunities, and there's cliches on both sides, right? Focus on your core competence, do what you're good at, and then on the other side it's like, well, just find do what the customer want. You have to make sure that the customer's always right. And I mean, the reality is that both situations are correct, and it's the instinct of leadership that really needs to navigate you through that. But it's I think for us it's been very much about kind of making sure that you do have market relevance, but being at least disciplined enough and persistent enough to kind of follow through, when you do see a market opportunity. And so, just maybe a final statement that, we are, the world leader in organic transistors and plastic liquid crystal, cells and optics. And so if anyone's out there that, wants to know more or do more with those sort of applications, then certainly, happy to talk today or at any point in the future. So thank you for your attention, and hope you enjoyed the talk.
Thank you, Mike. That was fantastic. Really good. Very enthusiastic talk as well. You. I presume you're happy to answer a few
Yeah,
questions.
if there's any questions, happy to answer. If there's any.
I guess I'm being a bit slow, but I wonder if you could explain to the layman how you change the refractive index using your screen technology. It's not immediately obvious to me as an engineer.
Yeah, it's how you do the refractive index. So try this one. Yeah, basically that's what liquid crystals do. So it's basically an anisotropic material, and so when you apply the voltage, it's not that you're not fundamentally changing the refractive index, and that you're just changing the orientation of the material, and so different phase. Yeah, so the in phase and out of phase, the refractive index will be different. And so, by controlling the polarization of light, so there are materials out there that you can actually do. They fundamentally, change their chemical structure by voltage, but that's not what we're doing. We're just changing the orientation, and we have an anisotropic material that can, kind of.
So, oh right. Extremely interesting, but you didn't mention very much about power sources, how voltage is, and how this, how you generate through the electrical impulses, the images, etc., in this film. And I'm really interested to know what size battery you might need, or can you explain that a little bit more? I didn't notice anything on there talking about power and the electrical input that you had to put into this film.
Sure. And it's different for the different applications, of course. For the liquid crystal displays, it would be the exact same way you would power a conventional liquid crystal display. So you have a backlight that is, basically attached to it. If it's a phone, it's a battery. If it's these aren't necessarily low power devices, I guess, is to your point. It's got the same power consumption as the equivalent in, silicon. For some of those other applications, like the lenses, the tintable films, those are actually very low power modes, because you switch the devices by voltage. There's not a lot of current drawn. So all the other applications I spoke about are actually quite low power. I mean, you still need to, but they're looking at them for AR VR devices, which would have very small batteries in there, and they're very particular on how much power how much power budget our component would take up. So we're not doing anything special, but ours aren't specifically low power, but for those lenses, definitely. You can definitely do that for the lenses. Definitely do that for the tintable films. The watch better would be fine.
Okay. Great talk. Thank you very much. Am I going to have to wait years and years to have my autofocus contact lenses?
Yes, I think so.
Is that a power supply problem?
Yeah, I mean, obviously putting it in the eye is, of course, another advantage. I mean, so we're really thinking about it as the glasses. I mean, I think there'd be other regulatory concerns of putting in the eye. But in some ways, it's easier in the sense that it's the biggest problem with lensing power is the bigger the lens, the more difficult it is to get focusing power. And so, but yeah, unfortunately, I think you're gonna have to wait a little while.
Yeah, and tintable.
Yeah, Mike, thanks for a really great talk. Some fascinating applications you had down here, by the way.
Sorry.
I was wondering, do you think we'll see N-type organic TFTs of a similar performance to P-type, so we can build some CMOS circuits
Yeah,
on your
interesting.
flexile substrate.
Yeah, great. I mean, that's probably the last time I spoke to you. You were talking, yes, the same question. Fundamentally, I mean, there are N-type, plastic, polymer semiconductors. Traditionally, they haven't been as stable. And I think it's because the biggest problem is specifically a water dopant, that it turns out that the N-type are more susceptible to than the P-type. Now, people are trying to, look at different synthetic routes around that, but right now, certainly the best-in-class materials are P-type, and they've been that way for a while. So, certainly there's never say never, but I can't. I don't have line of sight of it. That's for sure.
Just taking your first closing thought, a reminder of Richard Friend saying some while ago that, obviously extremely talented physicist and produced this technology with you and others. He said, well, he was in awe of engineers who could take what worked in the lab and create a product, and a product that could reach at scale.
Yeah. No, I think he's very aware of the effort involved. I mean, doesn't surprise me.
Okay, that's about it. Thank you very much, Mike, for an excellent talk. Thank you all for turning out on such a cold night as well and coming along to listen. It's a great pleasure to see you all here, and I hope you will return.